The normal force is the next force that we'll have in a class like this. The normal force, turns out, comes from when you try to sit objects on surfaces. The surfaces can generally be oriented in any direction, but the normal force is most common when we think of things like tabletops and stuff. So here's an example. Suppose we have a tabletop like this, and on top of the table we set a block. Now, the problem takes place near the surface of the Earth, so we know that the block here is going to have a downwards weight on it like that. In fact, the weight will be mg. So the question before us then is, if this block has a force, a downwards force on it due to the weight it's being pulled to the center of the Earth, why doesn't the block just start falling? You might say, oh, well, it's because there's a table in the way. So then the question is, well, what is it that the table does that prevents this block from falling? So once again, almost like in the rope video here, you have to look sort of microscopically here. You have to sort of peer into the table here and go, well, what would the table look like if we magnified it under a microscope? Once again, you'd see a chain like this, which would be a bunch of bonds if you want, and the bonds would be the bonds that are between the material that the table's made out of. Say if it's a plastic table, it would be like hydrogen and carbon bonds, that sort of thing, and the big hydrocarbons that, say, plastic are made of. But there'd be a bunch of bonds like this. So these things are meant to be the internal structure of the table in terms of bonds. And so what would happen then if you took a nice straight chain like this of material and you set a heavy object on it? So what happens then if you take a block like this that has a downwards weight, mg like that, and suppose you set this weight on this series of chains here that are the internal structure of the table, what would happen to that structure? Well, what would happen is the structure would begin to flex, where this is, say, the equilibrium position of the structure, maybe nice and straight. If you set a big heavy object on it, these bonds are going to flex downwards like this, right in the position where this heavy block is. So you set this heavy block like right in there like that. Here's your mg down like that. And so what you've done, you've actually stressed the internal structure of the table to support the weight of the block. And that's exactly where the normal force comes from. Because if these bonds here are sort of like little springs and they're really rigid and they'd really like to fall back against each other, or not fall back, but go back up to where their equilibrium position are, then this springiness or this stretching that just is going on here would like to restore itself back up to equilibrium. It's really just analogous to a trampoline. When you're standing on a trampoline like that, the trampoline would like to spring you back. This desire for this stressed out chain of table molecules to go back up again is exactly where the normal force comes from. So that upwards push is the normal force. And in this particular case, although this isn't always true, the normal force will exactly be equal to the weight that you've come down on the table with. So the weight is going to be equal to mg in this case here. But I'm going to loosely speaking put a little x by it, because then I'll put right next to it, this isn't always true. It's true in this case, but it isn't always true that the normal force is equal to mg, and we'll see some examples of that. So that's what the nature of the normal force is here. It has to do with surfaces, it has to do with setting an object on surfaces, and it has to do with the weight of objects stressing the internal structure of the object that you're setting on to the point where it actually deforms the structure, the molecular structure that would like to be back at equilibrium. And an object's desire to snap back to equilibrium is exactly where the normal force comes from. And so lastly, then, we'll just say also that in terms of the direction of the normal force, it's always perpendicular to the surface. That's where the word normal comes from. Normal is the mathematical term for perpendicular, and so the normal force would be always perpendicular to the surface that the object is sitting on. So just a couple examples here. If we go back to the table here, we won't always draw the molecular flexing that's going on, but we can draw in the normal force, which sits up like this, perpendicular to the surface. Or alternatively now, say we had a sloped surface like this, and a block was sitting on a surface like this, the normal force would not be straight up like that, because that's not perpendicular to the surface. You must always draw the normal force perpendicular to the surface, something like that. So that would be the normal force if a block was, say, setting on a inclined surface like that. And I'll just say also, this is the number one case here that students often get confused in. In this case here, the normal force is not strictly equal to mg. So it would be if it was on a flat surface, the way I described earlier, but it's not in this case. So there you go with the normal force. Stressing out surfaces, a force always perpendicular to the surface. Magnitude is a bit tricky, but we'll work on that, and that's the normal force.